Okay, so in this video, we're going to talk about a very important theorem in vector calculus, which is called the fundamental theorem of line integrals. So just in the same way that we have a fundamental theorem of integrals, which basically tells you that you can just evaluate a definite integral from one point A to a point B simply by integrating the function and then just evaluating that the value of that function at the points B and A. We're going to have the same kind of thing, but now we're going to apply it to the integral, or basically to the dot product of a vector field with some element that also depends on the curve C. So we can always do this as long as the vector field f is conservative, which allows us to find a scalar function, which we call the potential function, that satisfies this equation. So in this example, what we're going to do is we're going to evaluate this integral, this line integral, for the following vector field, which we have already seen in many videos before. And it is going to be integrated along the curve C. So this curve C is described by the parametric equation here. And it is going to go from t equals 0 to t equals 1. Now, in general, with this kind of question, there are three steps that we need to follow. So the first step is, of course, to show that the vector field f is conservative. Otherwise, every other step is just going to collapse and nothing is going to work. And we know that we can show that simply by proving that the curl is equal to 0. So this is the first step that we need to follow. The second step is going to be finding a potential function f such that the following relation is satisfied, which we already know how to do because we did it many videos ago. And the third step is just going to be to evaluate the function or evaluate the line integral based on this fundamental theorem of line integrals. So let's see how this goes. Let's start with the first step, which is showing that f is conservative. Now, when we introduced the notion of a conservative vector field, we also talked about how when you take the curl of a vector field of two variables, this essentially reduces to meeting the condition that this the partial derivative of the y component of the vector field over x is equal to this. So if we can actually meet this condition for this vector field, then we already proved that the vector field is conservative because this condition is automatically met with this. So let's differentiate the first component, the x component, with respect to y. So fx with respect to y is going to be 8y to the power 4 x cubed. And now we do the same for fy. So the y component differentiate with respect to x. So this becomes 8x cubed y cubed. And I just noticed I made a mistake. There should be y cubed because we subtract 1 from the power. So this becomes y cubed x cubed. And indeed, both of them are equal to each other, so that proves that the curl of f is 0, and that means that f is conservative. Alright, so now we can move on to the next step, which is finding a potential function that corresponds to this conservative vector field. So what we're going to do is we're going to write the gradient equals to the vector field. And this decomposes into two components. We have this partial with respect to x, partial of f with respect to y. And each of these components should be equal to the components of the vector field. So we have 2x cubed y to the power 4 plus x. And then 2x to the power 4 y to the power 3 plus y. And now the idea is to simply match this component by component. So basically this is going to be equal to that. So we have partial of f with respect to x is going to be equal to 2x cubed y to the power 4 plus x. Now we're going to integrate both sides of that with respect to x. So this is going to give us a function f of x and y. So integral of this with respect to x becomes x to the power 4 y to the power 4 over 2 plus x squared over 2 plus some function g of y. And we already discussed why that is, because you're integrating a function of two variables with respect to only one. Then instead of having a numerical constant of integration, you have a function functional constant of integration. Now we differentiate this with respect to the next variable in line, which is y. So the derivative of this expression with respect to y is going to be 2x to the power 4x cubed plus g prime of y. And this should all be equal to the second to the y component of the vector field, which is 2x4. This should actually be y here. So it's going to be equal to 2x4y cubed plus y. And then we notice that these two elements here are going to cancel out. So that means that g prime of y is equal to y. So that means that if we integrate both sides with respect to y, we get g of y is equal to y squared over 2 plus some numerical constant k. And now we go back down. So basically what is going to happen is we're going to have our scalar function, or our potential function for the vector field, is going to be equal to x to the power 4 y to the power 4 over 2 plus x squared over 2 plus y squared over 2 plus the numerical constant k. And now the third step is of course evaluating the line integral. So now that we found this function, we can write this line integral, and we can replace it by a to b of the gradient. And according to the fundamental theorem of line integrals, this is going to be equal to the potential function evaluated at the points r of a, sorry, this should be r of b, minus f at r of a. So what does that actually mean? Well, we already know what the potential function is. Now we're going to evaluate r at each of these points. So for b, what we're going to have, let me just write it down here. If we go back here, we know that the limit here on t is 1. So basically that's going to be our b. So we're going to evaluate this here. And this is actually it's going to have two components. So the x component is going to be the following. If we go back to the original question, we put 1 in here. So this is going to be 1 times cosine of 1 pi. So this is going to be minus 1, which is minus 2. And now if we go back here, so let me just check. Yep, that's minus 2. And here we're going to put 1. So that's going to become sine of pi on 2, which is equal to 1. And then we're going to have r at the point A. And we know the lower limit is just going to be 0. So now we're going to put that in here. So we have 0 times that. So that's just going to be minus 1. And 0 here, that's 0. So this becomes minus 1 and 0. So now what we do is we're going to evaluate each of these. So basically f, the potential function at the point RB, is just going to be the function at minus 2, 1. So these are the numbers that we're going to put into x and y. So if we evaluate this function here, what are we going to get? Well, this is going to be a little bit complicated. So we're going to have minus 2 to the power 4 times 1, 4 over 2. Plus minus 2 squared over 2 plus 1 over 2 plus k. And let's see what that gives us. So this becomes 21 over 2 plus k. And now we're going to evaluate the potential function at the point minus 1 and 0. So now we're going to put 0 here. So this is going to be 0. This is 0. So we have minus 1 squared over 2 plus k. And this is going to be equal to half plus k. And now the line integral. So the line integral of the vector field f dot product with dr is going to be equal to this minus that. So we have 21 over 2 plus k minus half And you notice that it didn't matter that we did not know what the numerical integration constant k was, because it always will cancel out in this expression. So whenever we have this, the k always cancels out. So basically this becomes 0. And now we have 21 on 2 minus half, so that's just going to be 20 on 2, which is 10. And that's it. That's the value of our line integral. And you notice that we found that simply by proving that f was a conservative vector field. Then we found a potential function f that corresponded to that vector field. And in the end, we just plugged that into the actual values of r in order to find what the value of that line integral was. But we did not need to actually evaluate f dot product with the r. We did not need to do that. We could have done it, of course, but it would have been a little bit more complicated than that, because we would have had to substitute this into this expression, which would have been just horrible. But here, by making use of conservative vector fields and potential functions, we were able to actually find the solution or the answer to this line integral in a rather simple manner. So the fundamental theorem of line integrals is quite useful for evaluating line integrals of this form.